In the last video, we saw this Lebesgue decomposition theorem basically tells you if you have two sigma finite measures, you can decompose one of them into a mutually singular part and an absolutely continuous part. And in this video, I'm going to finish the statement. Basically, I need to prove the uniqueness of this decomposition, and I'll briefly talk about why it's really useful in probability. Okay, so first of all, let's start with the following lemma. So the proof of this uniqueness, I'm really following a slightly different proof from Ken Davison's course notes. So let's look at this interesting lemma. So suppose I have a finite signed measure, let's call it rho, and suppose I have a sigma finite. Well, sigma finite is not really necessary here, but let's suppose I have another mu, which is positive measure. And if we know the sign measure is, first of all, mutually singular to mu, and is also absolutely continuous with respect to mu, well then, in fact, the only chance is this rho is actually equal to 0, okay? Well, the proof is really simple. So let's just start by recalling what's the definition of mutually singular. So by mutually singular, so this rho is mutually singular with respect to mu. It basically means there exists a null set. Let's say exists A so that the mu of A is equal to 0. Okay, and mu of A is equal to 0, and the complement, the A complement, is a null set. Okay, it's a rho null set. Okay. So here, the mu itself is a positive measure, so mu of A is equal to 0. It suffices for A to be a mu null set, and we just require the complement is a rho null set. Okay, that's just by definition. So what does it mean by A complement is a rho null set? So basically that means for every E subset of A complement, I have the rho of E is going to be equal to 0. So here rho is a sign measure, and for a sign measure in the null set basically means every subset has measure 0. Okay, not only A complement has measure 0, but also every subset. Okay, so automatically we have every subset of A complement is equal to 0. And now I have this mu is equal to 0. So here I have the other part, the mu of A is equal to 0. So by the absolute continuity, the rho is absolutely continuous with respect to mu. So we have rho absolutely continuous to mu. So that will imply the rho of A is also equal to 0. Okay. And in fact, not only that, okay, not only A is equal to 0. So here mu is a positive measure. So for every subset of A, okay, so for every F subset of A, okay, the mu of F is also going to be equal to 0. So that will imply the rho of F is also equal to 0. Okay, so like we briefly talked about this when we talk about the definition of absolute continuity. So if I have mu of something has measured 0, absolute continuity means the set A is also a rho null set. Okay, so that's basically we're just repeating the fact there. But anyway, so every subset of A also have rho measure 0. So if I give you any set E now, okay, so the rho of E, you can break it into a subset of A, so E intersect A, and a subset of A complement. And by what we just saw, both of them are going to be equal to 0. So rho is just equal to 0 everywhere. Okay, so that's finish this little lemma. And by this lemma, we can prove the uniqueness of the Lebesgue decomposition very easily. Okay, so uniqueness of Lebesgue decomposition. So suppose I have mu is equals to mu of A, where the A is the absolute continuous part and the mutually singular part. And suppose I have a different decomposition, let's call it mu of A prime plus mu of S prime. So let's assume for now this mu is finite. Okay, so let's assume it's finite, or I can say its absolute value is finite. So the mu of everything, it needs to be finite. Okay, so suppose I have these finite mu, then suppose I have two such decompositions, then what I can show using this equality is that I can move the absolutely continuous part to one side, so I have mu of A minus mu of A prime. That's equals to the nu of s prime minus nu of s. Okay, so you move the absolutely continuous part to one side and the singular part to one side. And you can convince yourself, well, if you have two measures that are both singular to mu, then their difference is, as a side measure now, is still going to be singular to mu. Okay, so let's call this rho. So this part tells you the rho is absolutely, well, it's mutually singular to mu. Okay, and here the nu a and nu a prime, they're both absolutely continuous with respect to mu, and you can convince yourself why rho is absolutely continuous with respect to mu as well. Okay, so that's something easy exercise. Okay, and from there now is pretty clear. Based on the lemma, I have a measure which is both absolutely continuous and mutually singular, and that just shows this rho has to be equal to 0. Okay, in other words, if it's equal to 0, then I get first nu of a is equal to nu a prime, and nu of s is equal to nu of s prime. Okay, so that's just based on this rho is equal to 0. And now, in the general case, if nu is sigma finite, okay, then I basically can pick a selection, a sequence of, say, kn, where the union of these kn is just the entire set x. And the nu, if I restrict each of these kn, I get a finite measure. Okay. So now suppose I have nu is equals to, again, if I have two decomposition, nu a plus nu s, and another way, write it as nu a prime plus nu s prime. Okay. Well, then one thing you can convince yourself is the nu a restrict to this kn plus the nu s restrict to this kn. You get a decomposition of the nu restrict to kn. Okay, and they are, when you restrict something, that's still going to be, well, absolutely continuous. Okay, so this first part is going to be absolutely continuous. You're restricting on a smaller set, so nu of a is actually much smaller than nu, is actually absolutely continuous with respect to nu. And nu of s itself is already mutually singular, so you restrict, you still get something that's mutually singular. Okay, and you do the same for the other side, so you have nu of a prime restrict to kn plus nu of s prime restrict to kn. So you basically, now you have a finite measure that can be written in these two ways. Okay, so by our proof for the finite measure, so for nu finite, okay, so we basically can say the absolutely continuous part is restricted to kn, that they have to be unique. Okay, so they have to be the same, and also you do the same thing for the singular part. So the mutually singular part, these two are the same. Okay, and because each of these is essentially just restricting to this kn, and by these kn, the union of these kn is equal to x, it's really easy to see the nu a is just equals to nu a prime, and nu s is equal to nu s prime. So this finish the uniqueness of this Lebesgue decomposition for the sigma finite case. All right, so now we finish this proof. Okay, so we now have this Lebesgue decomposition. Basically, every measure you can decompose it into a absolutely continuous part and a mutually singular part. And I want to spend some time talk about why this theorem is useful, or at least how it's used. Okay, so I want to talk about the decomposition of one type of measure we saw. That's basically the Brown measure on the real line, or is basically given by the Lebesgue-Stieltjes measure. Okay, so Lebesgue-Stieltjes measure. So if you recall, if the Lebesgue-Stieltjes measure is given by some mu of f, where f is let's say it's increasing, right continuous. By increasing, I mean not strictly increasing, but just increasing or non-decreasing. Okay, so f is strictly, it has to be right continuous, doesn't have to be left continuous. Okay, so let's say, well, this is our first measure. And on the real line, there's another measure, which is just, you all know this, the Lebesgue measure. Okay, so Lebesgue measure. So what does the Lebesgue decomposition tell us is the following. So the Lebesgue decomposition tells you each of these Lebesgue-Stieltjes measure mu of s can be decomposed as two parts. So first of all, you have a mu of a, okay, that's the absolutely continuous part, okay, and maybe I should just say AC, so absolutely continuous. And you have a mutually singular part, okay, so mu of s, okay, mu of ms, mutually singular part. So let's talk about each one of them a little bit more, okay. So of course, these two has to be Lebesgue-Stieltjes measure again, but the first one, the absolutely continuous part by the Radon-Nikodym derivative, this part is essentially given by an integral, okay? So this is essentially given by an integral of some function, okay? Some function respect to the Lebesgue measure, okay? So this is how the first part is defined, okay? So I'll talk about why this integral is important later, but let's look at the second part, the mutually singular part. So the mutually singular part, well, this is going to be still a Lebesgue-Stieltjes measure, okay? So it's actually, we can decompose it a little bit even further, okay? So this mu of the mutually singular part is equals to some mu of, let's say, G, where G is right continuous, non-decreasing. And in fact, this G, you can pull out all the discontinuity of this G, and you can make this G into a continuous part and a discrete part, okay? So a lot of time we can write it as two parts. So one thing we say is singular, and the second part is we call the discrete, okay? So usually this is called the singular part. And finally, I have a discrete part. And let's talk about each of these a little bit more detail. The singular part is essentially given by a, well, again, everything is Lebesgue-Stieltjes measure, so it's given by some function that's called h, okay? So here h, because it's mutually singular to the Lebesgue measure, so h is constant almost everywhere. Well, it's kind of piecewise constant, or you can say basically looks like a constant almost everywhere. It may not be the same constant, okay, but it looks really flat, okay? So one example is the counter function, okay? So on your assignment, I put this counter function. So they're only non-zero kind of, they're changing on the counter side, which has Lebesgue measure 0. So the mu of this counter function is going to be mutually singular with respect to the Lebesgue measure, because Lebesgue measure on the counter set is going to give you measure 0. Mu on the counter set complement give you 0 as well, okay? So that's what they look like. They're given by something that's really flat, okay? So they're flat except on a measure 0 set, okay? So that's possible. That counter set is one of the most typical example. And the discrete measure would, well, is basically given by a bunch of point mass, okay? So this is always going to be decomposed further as a bunch of the Dirac measures, so delta of xi, and you times some scalar, let's just say ci, okay? So on your assignment, I showed you, for example, you can take xi to be all the rational even, okay? This discrete set, these atoms can be dense even, okay? But that's going to be a discrete measure, okay? So the mu of this function is not very continuous, okay? So it's actually have a lot of junk discontinuity, but again, that's still mutually singular respect to the Lebesgue measure. And now you have these three parts, okay? So basically, let's just write it again. So the mu of f, you have three parts. So first of all, the absolutely continuous part, the singular part, and finally, you have a discrete part, okay? So why is this so important in probability? So if you think about what happens in probability, so let's say if mu of f is a probability measure, probability measure, okay, so apparently I don't know how to spell it. All right, so if it's a probability measure, then the natural thing you do is you do the following. So you assume this, we talk about this when we talk about the Lebesgue-Stieltjes measure, this f, you can make this f to have when you take the limit as x goes to negative infinity, that's going to be equals to 0. And when x goes to positive infinity of this f, it's actually give you 1. Okay, so in other words, you can think about this f of x is just the mu f of the set from negative infinity to x. Okay, so I think it's close x here. Okay, so if you have studied some probability theory, probably recognize this is the CDF of the distribution. Okay, and in the probability, a lot of the CDF come from an integral of something we call a PDF, a probability density function. And not everyone looks like that. Okay, for example, the Dirac measure, the coin toss, for example, those discrete measure, they don't have a PDF. Okay, but for continuous measure, they do have a PDF, and that in fact come from the absolutely continuous part. Okay, so for this mu of f, you have a mu of AC. Okay, so this part, it looks like the integral of the PDF function of x. Okay, if you know what I'm talking about. I'm not going to give out the definition here. So the absolutely continuous part is basically those probability measure that has a density function. Okay, those are the where you can have a PDF function essentially. And the second part is the mu of the singular. Okay, so this is a singular probability measure. Singular probability. And the most typical example is the countermeasure. Okay, so mu of the countermeasure is one example. Okay, it's kind of rare in probability theory, so there's not many. You probably didn't see it in probability theory. Okay, it's kind of rare to see these kind of examples. But last one is the discrete one. Okay, so mu of d. Okay, that's going to be a discrete one. So basically, a discrete probability is just something that only takes countably many values. Okay, so you can have coin toss, you can have all kinds of discrete distribution. So they only have masses at each point. Okay, so those are some combinations of the Dirac measure. Okay, so in other words, it looks like the probability of the xi is the ci. Okay, so that's what it is for the discrete measure. So every probability measure using this Lebesgue decomposition technique, you can decompose into these three parts. So if you want to study the probability measure, you can just break it into these parts and study them separately. That's why in the usual probability course, you start with the continuous part, you start with the PDF, and you start those continuous distribution, and you do the discrete. And of course, technically, there's a singular part which you rarely study. Okay, so that's how you use this Lebesgue decomposition theorem in probability theory. Okay, that's why it's a very useful theorem.